Okay, so now we're going to talk about some developments in atomic theory. So Dalton was the one who is credited with predicting that matter was made up of atoms, right? But the question is, what are atoms composed of? And are there things smaller than atoms? So let's start out with J.J. Thompson. So J.J. Thompson took a cathode ray tube and shot electrons down here. He didn't know what it was shooting down, right? He was discovering the electron. He shot a ray because he put some voltage between a cathode and an anode, two electrodes, and got a cathode ray, to go down a tube, right? And when it got down the tube, he measured where it landed. Well, he put it between two batteries, or rather two magnets, and some charged plates, and he found that if he varied the charge on these charged plates, he could bend this light. Can you see that cathode ray right there? Let me get my marker out here. It's bending the light. So when it has some voltage on it, it goes, whoops, bends up here like that, okay? And so that's how he measured the charge to mass ratio. Actually, that's what he did. It was the charge to mass ratio of ratio of a particle, right? Which we later described as an electron. So he discovered the electron and its charge to mass ratio. And he was in England. And then at the University of Chicago, Robert Milliken, who went to Oberlin, by the way, in Oberlin, Ohio, as an undergraduate, when he was in about 1908, I think, maybe 1909, Robert Milliken did this experiment. This is really a subtle experiment, and it's not really important, I think, that you understand exactly how it goes, but it's very cool. It's amazing to me that this guy had the patience and the tenacity to do this. Right? So he took this is an atomizer. He squirted little oil drops into this vessel, which he built. There's a little hole right here so he can see. There's his little telescope piece, right? He sticks his eye right here. There's his nose, right? There's his eye looking down into that, right? There's his neck, his hair, okay? He's looking down into that eyepiece, and he's watching these oil drops. So he takes a little atomizer, takes a little bulb, squirts it. Little tiny microscopic oil drops come in here. There's a plate up here and a plate down here, positively charged plate and negatively charged plate. And the oil drops come down through. And he set up an X-ray apparatus that went across here, okay? And it charged the particles, the oil drops. And he watched them. And he made it so that if he varied the charge on the plates enough, he could actually get these oil drops to stop from falling. Yes, to stop from falling, because it was a charged plate up here, right? So when they would come down, and he would get them to suspend in the air. And by doing that, he found that the charges of the different oil drops were like this. This is really cool. Look at this. The charges, it turns out, had very precise measures. So look, 1.6 times 10 to the negative 19, 3.2, that's exactly double of that, right? This is exactly triple of that. This is exactly quadruple of that. And he said, wait a second. Here's actually triple of that, right? He said, wait a second. These are all in very stepped charges. In other words, if I divide everything by the lowest number, I'm going to get 1, 3, 2, 4. That's also 3, right? So he took the smallest charge, divided everything by that, and found that he got whole number ratios. So by doing that, he found the actual charge of the electron. Now I've got some notes in this next slide. If Thompson knew so Milliken found the charge of the electron was 1.6 times 10 to the negative 19 coulombs. Amazing. Now, he knew from Thompson's work that the charge to mass ratio was this, right? And so he said, I can figure out how big I can figure out how big the mass of the electron. Amazing, right? Because the charge is 1.6 times 10 to the negative 19, right? And the ratio is 1.759 times 10 to the 11 coulombs per kilogram, right? Coulombs cross off, and we're left with kilograms, and boom, amazing. So he was able to extrapolate out the mass of the electron. Amazing. All right, so Thompson discovered the charge to mass ratio and discovered that we have electrons. Milliken at University of Chicago discovered the charge of the electron and extrapolated from it the mass of the electron. And then let's look at some of their the theories of how they thought these things went. There's the Plum pudding model, right? So Thompson thought this is plum pudding. It's really like a soft cake and a moist cake. I guess that's what that says here. Moist cake. Go back to red. And he suggested that the atoms were made of charged particles that were pluses and minuses all mixed in, right? Like that's your plum pudding. Nagoya, I'm not sure how to pronounce this name here, and I think this is Japanese. He said that that it was going to be more like Saturn, right? So you've got this picture of Saturn here, where you've got the pluses in the middle and then negatives on the outside. And of course, he was, more correct. All right. So these are the models of the atom. Now, Rutherford. I don't remember where Rutherford was, but Rutherford took gold foil. Here's a gold foil here. Little piece of gold foil, very thin, hammered, essentially very, very thin, right? Nearly one, not an atom thick, but very, very thin gold foil. And he shot alpha particles, a beam of alpha particles through it, and he found that most of them went straight through. Most alpha particles pass straight through the foil. Wow, are you serious? Some get bounced off. And so he had this a luminescent screen all the way around it and found that some bounce that way, some bounce and reflect back, some go here, but most of them go straight through. And so he said an atom is mostly empty space. Wow. So here's another example of that. Here's the gold foil and your alpha particles, which are pretty big. They're essentially helium nuclei. They're just mostly going to go straight through, right? And so here's the nucleus of an atom. Here's another nucleus of an atom. Here's another nucleus, right? And if you shoot an alpha particle, most of them go straight through. And that's how he said that atoms are mostly empty space. And that was Ernest Rutherford. All right. Other important discoveries were isotopes. That is, some atoms in an element have different masses, which is inconsistent with what Dalton said. That is, some of them have this number of neutrons, some have those number of neutrons. He didn't know that they were neutrons. Neutrons were discovered later by James Chadwick. Okay, uncharged subatomic particles with a mass approximately the same as that of protons. All right, so that's the development in the early 1900s of the theory of the atom, and it's important historical context. We are going to get most of our value from other places. We're going to define protons and neutrons and electrons and isotopes and so on in future conversations.